So earlier we discussed about wireless channel, why it is important to understand wireless channel, how this channel is different from the other types of channels, and the main important feature of wireless channel, that is multipath propagation, where we said that if we have a transmitter and at the receiver we will receive multiple reflected copies of the signal, and at the receiver what we get is the cumulative effect of all these copies, where all these copies they can add constructively or they can add destructively, resulting in the signal strength fluctuations. And this signal strength fluctuations is what we call as fading. Now, if we want to characterize fading, it can be characterized into two types: the large scale fading and the small scale fading. The large scale fading is the one which captures the effect of signal strength fluctuations over large separation distances. Whereas the small scale fading, they captures the effect of signal strength fluctuation over a few wavelength. For example, we saw that when frequency is 900 megahertz, we get lambda by 2 to be 15 centimeter, which is very small. And the signal strength fluctuations over this lambda, they are captured by the small scale fading. So further, in small scale fading, it is characterized into time selective fading. So what we mean by time selective is that, as the word also indicates selective, that there is a selection of time. So what we mean by this is, let's say this is the time axis and this is the received power at a distance d at time t. So there is a fluctuations of the signal strength, and there is a time, this time, where the signal experience no attenuation, and there are times when the signal experience huge attenuations. So in short, we say that there is a selection of times where the signal experience huge attenuation and where a signal experience no attenuation. The next is space selective, and it is rich scattering and poor scattering. What we mean by this is, we have an environment, for example, just like a city center where there are number of buildings around us, and we receive a signal. There are a lot of reflections from many reflectors, and we receive signal from each and every direction. So this kind of scenario is a rich scattering scenario because there are many reflections of the signal. Whereas the other scenario, poor scattering, is the scenario where we have a transmitter and a receiver, and there is only one hill and we have one reflected path from the hill. So that means poor scattering is the scenario where we have either one or maybe two reflections. So next is the frequency selective fading. Because we want to see the variations of signal with the frequency, we call it as frequency selective fading. So when we talk about large scale fading, so we have path loss, which is the attenuation model, and this captures the effect of signal strength fluctuations as a function of transmitter and receiver distance separation. So based on what is the separation between the transmitter and the receiver, what is the average signal strength across this distance. So the next is shadowing. It captures the local mean over this distance, and it improves the effects that are captured by the path loss model, because both are the predictor of average signal strength, but this is the predictor of average signal strength across a distance d, whereas the shadowing, it also computes the local mean over this distance d. So next in this figure, if we see that this is the received power PR function of d, and this is the separation distance between the transmitter and the receiver. So this green line, it shows the instantaneous fluctuations of the signal over a very few lambda, because there is a huge fluctuation in a small lambda. So we call this fading as small scale fading. On the other hand, if we take the average of this green instantaneous fluctuating signal strength, we get large scale fading, which is shown by the red line that shows the average signal strength at a particular distance d. And when we talk about large scale fading, it is usually measured around 5 lambda to 40 lambda, which is very higher than lambda by 2. So therefore we call this as large scale fading. So next, let's look at the aspects of large scale fading. So large scale fading is caused by the power dissipation. So what we mean by power dissipation is that if we have a transmitter and it is radiating energy in equal directions, so we will have a globe. And if we assume that the receiver is present here, and since the size of the receiver antenna is fixed, a very small fraction of energy is received by this receiver at this location, because the globe is bigger and the power is divided across the globe. So when we move closer to the transmitter, let's say at this location, but now here the globe is smaller and we will receive a significant amount of power at the receiver. So this is the meaning of power dissipation. That is, as we go away from the transmitter, we will receive less energy, whereas on the other hand, when we are closer to the transmitter, we will receive more radiated energy. And these effects of large scale, they captures the effect of propagation channel. So next, if we assume that there is a same path loss at a given transmitter and receiver distance, that is, if the receiver is here at this location and this is the distance d. Now if the receiver is here at this location, this is also a distance d, and if the receiver is here at this location, this is also a distance d. So the path loss at each of these locations and across this globe will be same, because it is a function of distance between the transmitter and the receiver. And only if we do not assume that there is no shadowing in this model. And where this is applicable, how this is useful, that assuming that equal the same path loss at a distance d, why it is so useful? Because if we consider, so let us take this example. So if we have this received signal strength PR at a distance d, and this is distance d. So as we are going away from the transmitter, the received power is decreasing. And let's assume there is a threshold received power gamma, and this is the distance d1. So there can be two possible cases. PR of d at distance d is greater than gamma, and PR at a distance d is less than gamma. So based on this, we have two regions. One is this region, and this region is known as the coverage region, because the signal strength received at the receiver is greater than the minimum threshold strength required at the receiver, that is gamma, which means this case. And this is the no coverage region, where the received signal experienced by the receiver is very less than the minimum required level. So the user is not satisfied in this region, whereas the user is satisfied in this region. So as a result of this model, it helps us to calculate this D1. So till which region the user should be present so that the required signal strength quality is greater than the gamma. So next, the signal strength variation in a large scale fading occurs for 100 to 1000 meters when we are talking about path loss, and 10 to 100 meters for shadowing effect. And these propagation models, they can be well approximated by a ray tracing model, which is good when the number of multipaths are small. And the next model is the statistical model. If we have a very large number of multipaths, we rely on the measurement data, and then based on that measurement data, we apply curve fitting, and then from the curve fitting, we develop some parameterized model. So these models are known as statistical models. So next, if we look at the propagation losses with the transmitter and the receiver separation distance d. So this is the received power at a distance d, which is represented in dBm, and this is the transmission receiver separation distance d. So if we look at the path loss first, since path loss indicates that it is the average signal strength with distance d. So as we are increasing the distance, there is a monotonic decrease in the received power at the receiver. So now the shadowing, it captures the local mean across the average received signal strength. So this slowly varying dashed line represents the shadowing, effect of shadowing. That is the fluctuations in the received signal due to shadowing. And then the instantaneous fluctuations over this shadowing is known as small scale fading, which occurs with a very few change in lambda. So thus we have three aspects. One is the path loss, which is the average decrease in the signal strength. The other one is the shadowing, which is the slowly varying signal strength. And then we have small scale fading, which shows the instantaneous signal strength. So at the receiver, when we calculate the loss, we take the cumulative effect of these three, that is small scale fading, shadowing, and path loss.